All right, get ready because today we're diving deep.
Into amines and diazonium salts.
You've sent over some fascinating material on these organic compounds, and
Yeah.
honestly, I'm excited to see what nuggets of knowledge we uncover.
I think you're going to be surprised by just how much these compounds impact our daily lives
Oh, really?
without us even realizing it.
Interesting.
From the smell of fish to the colors in our clothes,
Hmm.
amines and diazonium salts are hidden players in so many things we encounter.
Okay, that definitely piques my curiosity.
Yeah.
So let's start with amines.
Yeah.
They're often described as derivatives of ammonia, but what exactly does that mean? Is it like ammonia with a fancy makeover?
That's a pretty good way to think about it. Ammonia, with its nitrogen atom bonded to 3 hydrogen atoms,
Right.
is kind of like the basic template.
Okay.
Amines come along and swap out 1,
Yeah.
2, or even all 3 of those hydrogens with something a bit more elaborate, alkyl or aryl group.
Alkyl and aryl groups. Those are those chains and rings of carbon atoms.
Right. Exactly.
Yeah.
Alkyl groups are like little branches extending out from the nitrogen atom,
Oh.
while aryl groups are those elegant ring structures like benzene.
So it's like ammonia is the basic t-shirt. And amines are all about adding those cool patterns and designs with alkyl and aryl groups.
Right.
But why does it matter how many hydrogens are replaced? It's not just about fashion, right?
Definitely not. Chemists classify amines as primary, secondary, or tertiary,
Okay.
based on how many hydrogens are replaced.
Yeah.
This classification is crucial because it directly influences the amines' properties and how they behave in reactions.
Sure.
A primary amine, with only 1 hydrogen swapped out,
Okay.
will react quite differently from a tertiary amine where all 3 hydrogens are
Like
replaced.
different dance moves depending on how many partners the nitrogen atom has.
I like that analogy. And speaking of names,
Yeah.
chemists can be quite particular about how they label these molecules.
Oh, I know all about that. They have their own special language.
Yeah.
But let's be honest, sometimes those chemical names can sound like something out of a science fiction movie.
True, but there's a method to the madness.
Okay.
Chemists use both common names
Uh-huh.
and the more systematic IUPAC system to identify amines.
Okay.
Common names are a bit like nicknames.
Right.
They're based on the groups attached to the nitrogen atom.
Okay.
For example, if you have a methyl group attached to ammonia,
Uh-huh.
it's simply called methylamine.
Simple and to the point. I like it.
Yeah.
But then we have the IUPAC system,
Right.
which is probably where things get a bit more complicated.
It does get a bit more systematic,
Okay.
but it's all about providing a unique and unambiguous name for every compound.
Okay.
For primary amines,
Uh-huh.
we replace the E at the end of the parent alkane name with -amine.
Got it.
So CH3NH2, which is derived from methane,
Right.
would be called methanamine.
Okay, I'm starting to see the pattern here.
Right.
But what if we have more complex amines like those with multiple substituents? How do we handle those naming conundrums?
That's where the locant N comes in.
Yeah.
We use N to indicate that a substituent is attached directly to the nitrogen atom.
Oh.
So for instance, CH3 NHCH2CH3
Okay.
would be named N-methylethanamine
N-methylethanamine.
because we have a methyl group attached to the nitrogen of an ethane molecule.
So we're being super specific about where those groups are hanging out in the molecule.
Exactly.
It's all about location, location, location.
That's right.
Now, let's say I want to create some ethanamine.
Okay.
What are my options? What tools do chemists use to make these compounds?
Well, there are several methods,
Yeah.
each with its own strengths and weaknesses.
Uh-huh.
One common approach is to start with a nitro compound
Okay.
and reduce it.
Reduce it.
Imagine adding hydrogen gas in the presence of a catalyst like platinum, palladium, or nickel.
Platinum, palladium, or nickel.
This process essentially transforms the nitro group NO2 into an amine group NH2.
It's like giving the molecule a hydrogen makeover.
Right.
Turning that nitro group into a lovely amine.
Exactly.
What other methods do chemists have up their sleeves?
Another one is hemolysis of alkyl halides.
Okay.
Here we use ammonia to displace a halogen atom in an alkyl or benzyl halide.
So,
Ammonia swoops in,
Yeah.
clicks out the halogen, and takes its place, forming an amine.
sounds like ammonia is quite the force to be reckoned with.
It is.
But I imagine this method might have some drawbacks.
Yeah.
Can't be that simple, right?
You're right. It's not always so straightforward.
Okay.
One issue is that aminolysis can lead to a mixture of different amines,
Uh-huh.
primary, secondary, and even tertiary.
Okay.
It can be a bit of a chemical free-for-all,
Right.
making it less ideal if you're aiming for a specific type of amine.
So it's like a chemistry party where you might not always get the guest list you were hoping for.
Yeah, exactly.
Are there any methods that offer more control over the outcome?
Absolutely. The Gabriel phthalimide synthesis is
Yeah.
a go-to method for making primary amines. It involves a series of steps,
Wow.
but it reliably yields a primary amine,
Right.
making it a valuable tool for chemists.
It's like having a specialized tool for a specific job.
Yeah.
What other methods should we know about?
Another interesting one is the Hoffman-bromamide degradation reaction.
Okay.
This reaction is unique because it actually shortens the carbon chain while creating a primary amine.
Oh.
You start with an amimide, treat it with bromine and a base,
Okay.
and through a rearrangement process, you end up with a primary amine with one less carbon atom.
It's like a carbon shrinking magic trick.
It is.
Are there any other notable methods for preparing amines?
Yes, we also have reduction of nitriles and amides.
Okay.
These reactions utilize lithium aluminum hydride, LiLH4,
LiLH4.
or catalytic hydrogenation to produce amines.
Okay.
They're particularly useful when you need to lengthen the carbon chain in the amine.
So we've got a whole toolkit for building and modifying amines. Now let's shift gears a bit and talk about what makes amines unique.
Okay.
What are their personalities like?
Yeah.
So to speak.
Well, one of the first things you might notice about some amines
Okay.
is their odor.
Over.
Some of them, especially the lower molecular weight ones, have a rather fishy smell.
Fishy smell.
As you go up in molecular weight,
Uh-huh.
the odor tends to become less intense or even disappear.
So it's a range of aromas from fishy to,
Yeah,
well, not so fishy.
right.
What other characteristics stand out?
Their solubility is another important factor.
Okay.
Some amines are quite soluble in water,
Uh-huh.
while others are not.
Okay.
It all comes down to their ability to form hydrogen bonds with water molecules.
Right.
The stronger the hydrogen bonding,
Yeah.
the more likely the amine is to dissolve in water.
It's like some amines are eager to mingle with water, while others prefer to keep to themselves.
Exactly. And then there's the boiling point,
Okay.
which is influenced by those intermolecular forces. Amines generally have higher boiling points than alkenes of similar molecular weights
Uh-huh.
because they can engage in hydrogen bonding.
Okay.
However, the strength of that hydrogen bonding depends on whether the amine is primary, secondary, or tertiary.
So the more hydrogen bonding partners an amine has,
Yeah,
the higher its boiling point?
precisely. Primary amines with 2 hydrogens available for hydrogen bonding tend to have the highest boiling points.
Got it.
Then come the secondary amines with 1 hydrogen for bonding, followed by tertiary amines, which can't form hydrogen bonds with each other, giving them the lowest boiling points among the 3 types.
It's like a molecular dance party, where the more partners you have, the harder it is to leave.
Right.
But beyond their physical characteristics, I've heard that amines are quite reactive.
They are.
What's the story there?
Amines are indeed quite versatile when it comes to their reactivity. A lot of that has to do with the lone pair of electrons on the nitrogen atom. These electrons make amines good nucleophiles.
Okay.
Meaning they're attracted to positively charged centers in other molecules.
So they're like little electron magnets,
Right.
always seeking out positive charges to interact with.
Yeah, good way to put it.
Okay.
And one of the most fundamental reactions of amines is their ability to act as bases.
As bases.
They can readily accept a proton H+ from an acid forming an ammonium salt.
It's like amines are those generous friends who are always willing to share their snacks.
Yeah.
In this case, they're sharing electrons.
Sharing electrons, exactly.
But how readily they share those electrons must depend on a few factors.
It does.
Like?
You're absolutely right. The strength of an amine's basicity is influenced by several factors,
Well-
including inductive effects,
Okay.
solvation effects, and steric hindrance.
Okay, let's break down those terms.
Okay.
What exactly are inductive effects?
Inductive effects refer to the electron-donating or electron-withdrawing nature of the groups attached to the nitrogen atom.
Okay.
For example, alkyl groups tend to donate electrons, making the lone pair on nitrogen more available for sharing, thus increasing basicity.
So alkyl groups are like supportive friends,
Yeah,
encouraging the amine to be more generous with its electrons.
exactly.
What about solvation effects? How do those come into play?
Solvation effects come into play when an amine accepts a proton
Okay.
and forms a positively charged ammonium ion.
Right.
How well this ion is stabilized by the surrounding solvent molecules, like water,
Okay.
influences the amine's willingness to accept that proton in the first place.
So it's all about how comfortable the ammonium ion feels in the solvent.
Right.
The more comfortable it is,
Yeah,
the more likely the amine is to accept that proton.
exactly. And finally, we have steric hindrance,
Steric hindrance.
which is all about the bulkiness of the groups around the nitrogen atom. If those groups are very large, they can physically hinder the amboline's ability to accept a proton.
So it's like trying to fit into a crowded elevator.
Exactly.
Sometimes size does matter in chemistry.
It does.
Can you give me some examples of how these factors affect the basicity of real amines?
Absolutely. Let's consider alkylamines.
Alkylamines.
They're generally stronger bases than ammonia
Okay.
because those alkyl groups donate electrons,
Right.
increasing the electron density on the nitrogen. But when it comes to arylamines like aniline,
Okay.
they're actually weaker bases than ammonia.
Hold on. I thought more groups generally meant stronger basicity.
Yeah,
Why is aniline an exception?
that's where resonance comes in.
Resonance.
In aniline, the lone pair of electrons on the nitrogen isn't just sitting there on the nitrogen. It's delocalized into the benzene ring through resonance. This delocalization makes the lone pair less available for accepting a proton,
Okay.
decreasing the anine's basicity.
It's like the electrons are being pulled in different directions,
Right.
making them less available for sharing.
Yeah,
Fascinating how these subtle electronic interactions can have such a big impact.
it is.
Now, I'm curious to see how these amines behave in actual reactions.
Yeah.
They're not just sitting around, right?
No, they're not.
They must be involved in all sorts of chemical transformations.
You're absolutely right. Amines are key players in a wide variety of reactions.
Okay.
One common one is alkylation,
Alkylation.
which involves adding more alkyl groups to the nitrogen. Think of it as expanding our dance floor and bringing in even more partners.
Sounds like a lively party. What other reactions should we know about?
Well, another essential reaction is acylation,
Acylation.
where an amine reacts with an acid chloride,
Okay.
anhydride, or ester.
Okay.
This reaction results in the formation of an amide,
Okay.
with an acyl group taking the place of a hydrogen atom on the amine.
So it's like adding a stylish new accessory to our amine molecule.
That's a good way to put it.
Are there any reactions that are particularly useful for identifying specific types of amines?
Absolutely. The carbylamine reaction
Okay.
is a classic test for primary amines.
Right.
When you heat a primary amine with chloroform and a base,
Chloroform and a base.
you get an isocyanide,
Okay.
which has a very distinctive and, let's just say, not so pleasant smell.
So it's like a chemical fingerprint that only primary amines can leave behind.
It is.
I guess chemists don't mind a bit of a strong odor if it helps them solve a mystery.
That's right.
And then there's the reaction with nitrous acid,
Yes.
which is particularly intriguing because it helps us differentiate between primary, secondary, and tertiary amines.
Right.
Each type reacts differently with nitrous acid,
They do.
giving us a clue to their identity.
Exactly.
So it's like nitrous acid is a chemical detective, interrogating our amines and revealing their true nature.
I like that analogy. For
Okay.
instance, primary amines react with nitrous acid to form diazonium salts. Okay.
Which are quite unstable and quickly decompose, releasing nitrogen gas.
So primary amines are the ones that make a dramatic exit,
Yes.
leaving behind a trail of nitrogen gas.
That's a good way to visualize it.
Secondary amines, on the other hand, react with nitrous acid to form N-nitrosoamines,
Right.
which are oily yellow liquids.
Yes.
While tertiary amines typically don't react at all.
Exactly.
So each type of amine has its own signature response to nitrous acid.
You do.
It's like a chemical personality test.
That's right. And then we have the reaction with aryl sulfonyl chloride,
Okay.
also known as Hinsberg's reagent.
Hinsberg's reagent.
This reaction is incredibly useful for distinguishing between the different classes of amines.
Okay.
Primary amines react to form sulfonamides that are soluble in alkali.
Okay.
Secondary amines form sulfonamides that are insoluble in alkali.
Okay.
And as with nitrous acid, tertiary amines don't react at all.
So it's like Hinsberg's region is sorting our amines into neat little categories based on their reactivity. Exactly. Now let's talk about electrophilic substitution reactions.
Okay.
Especially with aromatic amines like aniline.
Aniline.
The anamine group in aniline acts as a powerful activator and directs incoming groups to specific positions on the benzene ring,
Okay.
mainly the ortho and para positions.
So the aniline group is like a traffic director.
Right.
Guiding the incoming groups to their designated parking spots on the benzene ring.
I like that.
Right.
But this high reactivity of aniline
Yeah.
can sometimes be a bit too much of a good thing.
Sure.
To manage it, chemists often protect the amine group by acetylating it,
Protecting it.
which means reacting it with acetic anhydride to form an amide.
Okay.
This amide is much less reactive
Right.
and allows for more controlled reactions.
Bro.
Once the desired transformation is complete,
Okay.
the protecting group can be removed, restoring the amine group.
It's like putting a temporary shield on the amine group to keep it out of trouble until the main reaction is done.
Exactly. Now, are you ready to shift gears and enter the world of diazonium salts?
Absolutely. They've been lurking in the background of our alumine discussions, and I'm definitely ready to explore these intriguing compounds in more detail.
Well, get ready for some fireworks. Diazonium salts are some of the most reactive and versatile compounds in organic chemistry.
Oh?
They have this general formula of Rn2 plus X,
Okay.
where R is an aryl group,
Uh-huh.
and X can be a variety of anions,
Okay.
like chloride, bromide, hydrogen sulfate, or even tetrafluoroborate.
So it's like they have this core identity with the N2 plus group, but they can switch up their style depending on which anion they're partnered with.
Exactly. And we name them based on their parent hydrocarbon and the anion attached.
Okay.
For example, if you have a benzene ring with a diazonium group and a chloride ion,
Right.
it would be called benzene-diazonium chloride.
Okay, that naming system seems pretty straightforward.
Yeah.
But you mentioned they're highly reactive.
Yeah.
What makes them so special in that regard?
Diazonium salts are renowned for their ability to undergo reactions where the diazonium group acts as a leaving group.
Okay.
This means it can be easily replaced by other groups, allowing chemists to introduce a wide range of substituents onto that aromatic ring.
So it's like they're holding a placeholder position that's open to a whole cast of different characters.
That's an excellent analogy.
Yeah.
Now, you might be wondering how we even make these remarkable diazonium salts in the first place.
That's exactly what I was thinking. They sound so important, so I'm curious about their origin story.
The most common way to prepare them is through a process called diazotization.
Diazotization.
We start with a primary aromatic amine,
Okay.
like our friend aniline,
Right.
and react it with nitrous acid at low temperatures.
Citrus acid.
The nitrous acid is usually generated in situ
Yep.
by mixing sodium nitrite with a strong acid like hydrochloric acid.
So it's a carefully controlled reaction to create these reactive diazonium salts.
It is.
I'm sensing a theme here. Chemists seem to be quite fond of controlling reactions.
They are.
It's important to keep the temperature low because diazonium salts are quite unstable
Yes.
and tend to decompose at higher temperatures.
Right.
Got to handle with care. But once we have these precious diazonium salts, what can we actually do with them? What kind of reactions are they known for?
Oh, the possibilities are vast. Let's start with reactions where the nitrogen departs,
Okay.
taking its two nitrogen buddies with it,
Right.
leaving a vacancy on the aromatic ring for another group to fill.
It sounds like a molecular game of musical chairs with the diazonium group always leaving an empty seat.
Exactly. One of the classic reactions is the Sandmeyer reaction,
Sandmeyer reaction.
where we use cuprous salts as catalysts to introduce halide ions like chloride, bromide, or even a cyanide group onto the benzene ring.
So copper plays a key role in facilitating these substitutions.
It does indeed.
Yeah.
There's also the Gatterman reaction,
Gatterman reaction.
which is similar to the Sandmeyer reaction but uses copper powder as a catalyst instead of copper salts.
Okay.
Both reactions achieve the same outcome. But the Sandmeyer reaction generally gives better yields.
So chemists have a couple of different tools in their toolbox for making those halogen substitutions.
They do?
What about other groups? Can we introduce those as well?
Absolutely. We can replace the diazonium group with an iodide ion
What?
simply by treating the diazonium salt solution with potassium iodide.
Potassium iodide.
However,
Introducing a fluoride ion requires a slightly different approach.
okay,
We first reacted the diazonium salt with fluoroboric acid,
fluoroboric acid.
which forms a diazonium fluoroborate precipitate.
Uh-huh.
Heating this precipitate then gives us the desired aryl fluoride.
So each halogen has its own preferred method of entry.
That's right.
What if we want to simplify things and just replace the diazonium group with a simple hydrogen atom?
Yeah.
Is that even possible?
Yes, it is. It's essentially a reduction reaction.
Okay.
We can use mild reducing agents like hypophosphorus acid
Hyperphosphorus acid.
or even ethanol to reduce the diazonium salt back to the parent end. It's like undoing the diazotization process and going back to the basics.
Exactly. Now,
Sure.
let's talk about introducing an OH group.
Okay. An OH group.
This one's a bit tricky because it requires careful temperature control.
Temperature control.
If we let the diazonium salt solution warm up to around 283 K,
283K.
it undergoes hydrolysis,
Okay.
replacing the diazonium group with an OH group and forming a phenol.
So temperature is key for creating those valuable phenols.
It is.
It's like a Goldilocks situation. Not too hot,
Right.
not too cold,
Yeah,
but just right.
exactly. And if
Yeah.
we want to introduce a nitro group,
A nitro group.
we can heat the diazonium fluoroborate with aqueous sodium nitrite in the presence of copper.
What?
This reaction replaces the diazonium group with a nitro group,
Okay.
giving us another way to modify our aromatic ring.
Wow. So many possibilities.
There are.
It's amazing how much control we have over these substitutions.
It really is. And remember, diazonium salts are particularly valuable because they allow us to make compounds that are otherwise difficult to synthesize directly.
Right.
For example, making aryl fluorides and iodides through direct halogenation is quite challenging.
Okay.
But diazonium salts provide a convenient workaround.
It's like they're opening up new pathways in chemical synthesis, allowing us to create molecules that we couldn't easily access before.
Exactly. But hold on, there's more. Diazonium salts aren't just limited to those substitution reactions where the nitrogen departs.
Oh.
They can also participate in reactions where the diazo group sticks around,
Okay.
leading to the formation of azo compounds.
Okay, now I'm really intrigued. Azo compounds. Tell me more about these intriguing molecules.
Right.
What's their story?
These reactions,
Okay.
known as coupling reactions,
Linoleic reactions?
involve the diazonium salt reacting with electron-rich aromatic compounds,
Okay.
typically phenols or aromatic amines.
Okay.
The diazonium salt essentially attacks the electron-rich ring, forming a new nitrogen double bond
Okay.
and creating a beautiful extended conjugated system.
So we're connecting two aromatic rings together through a nitrogen bridge.
Right.
What's so special about these azo compounds? Why are chemists so interested in them?
Oh. Well, that extended conjugation in azo compounds often leads to some striking visual effects.
Oh, really?
They tend to be intensely colored,
Okay.
making them incredibly useful as dyes and pigments
Wow.
in a wide range of applications, from textiles and paints to even food coloring.
Wow. So we're talking about the chemistry of color.
We are.
It's amazing to think that these molecular structures are responsible for the vibrant hues we see all around us.
It really is.
Oh.
One classic example is the formation of pihydroxyazobenzene,
Hydroxyazobenzene.
a bright orange dye.
Okay.
It's created by coupling benzene and diazonium chloride with phenol.
Interesting.
Similarly,
Yeah.
coupling benzene and diazonium chloride with aniline gives us p-aminoazobenzene,
P-aminoazobenzene.
a yellow dye.
It's incredible how diazonium salts bridge the gap between chemistry and the art world,
Yeah.
allowing us to create such a spectrum of colors.
It's a beautiful example of how fundamental chemical principles can lead to such practical and visually stunning applications.
Okay, let's take a step back and try to synthesize all the amazing information we've covered about amines and diazonium salts.
Okay.
We started by exploring amines, those ammonia derivatives where one or more hydrogens are replaced by alkyl or aryl groups.
Right.
We learned about their classification as primary, secondary, and tertiary,
Yeah,
and how this classification affects their properties and reactivity.
exactly.
We then delved into the fascinating world of amine synthesis, uncovering the various methods chemists use to create these versatile compounds, from reducing nitro compounds to utilizing elegant reactions like the Gabriel phthalimide synthesis and the Hoffman bromamide degradation reaction.
We did.
We also explored the factors that influence an amine's basicity, including inductive effects, solvation effects, and steric hindrance. It's amazing how these subtle molecular interactions can have such a significant impact on an amine's willingness to share its electrons.
It is fascinating, isn't it?
And of course, we couldn't forget those key reactions that amines participate in,
Yeah.
such as alkylation, acylation, and the carbolamine reaction,
Right.
which is like a chemical fingerprint for primary amines.
Uh-huh.
We also talked about their reactions with nitrous acid and aryl sulfonyl chloride,
Right.
which help us distinguish between the different types of amines.
Yes.
Then we've entered into the realm of diazonium salts, Those reactive intermediates derive from primary aromatic amines.
We did.
We learned about their preparation through diazotization and their remarkable versatility in undergoing both substitution reactions where the diazonium group is replaced and coupling reactions where it's retained, leading to the formation of those colorful azozo compounds.
Exactly.
Diazonium salts truly showcase the ingenuity and power of organic chemistry, allowing us to make compounds that are otherwise difficult to access and opening up new avenues for chemical
They
synthesis.
really,
It's been an incredible journey through the world of amines and diazonium salts.
it has.
I'm struck by how these seemingly abstract concepts in organic chemistry has such profound implications for our daily lives,
Right.
from the medicines we rely on to the vibrant colors that surround us.
Absolutely a testament to the power of scientific exploration and the interconnectedness of the chemical world.
And who knows what future discoveries await us in the realm of amines and diazonium salts.
I know.
Perhaps new amine-based materials with unprecedented properties or novel Abanon dyes with even more dazzling and durable colors.
The possibilities are truly endless.
This deep dive has definitely sparked my curiosity, and I'm excited to see what the future holds for these fascinating compounds.
That's what it's all about, nurturing that scientific curiosity and never stopping exploring.
Well, on that note, I think it's time to wrap up this deep dive into the world of amines and diazonium salts.
Okay.
Thanks for joining us, and until next time, keep exploring the wonders of chemistry.